Hello and welcome to the Crocodile Specialist Group Virtual Drone Workshop. My name is Andrew Ortega and I'm the Research Coordinator of the UF Unmanned Aircraft Systems Research Program. Our Program Director, Dr. Ray Carthy from the U.S. Geological Survey, and I have prepared this brief general introduction to drones. We hope you find it informative as you contemplate integrating drones into your work. We'll start out by asking, what are they? You may have heard of these other names for drones. We commonly call them unmanned aircraft systems since they consist of the integrated aerial platform, sensors, data storage, and onboard data processing. There are a few different types of unmanned aircraft systems. This image shows a quick comparison between the main two categories of multi-rotors and fixed-wing. Our rule of thumb is to use multi-rotors for acres and fixed-wings for hectares. Fixed-wings raise issues of line of sight because it is difficult for a single pilot to maintain the aircraft in his field of view for the entirety of the flight. A hybrid approach of these two systems is known as VTOL, or vertical takeoff and landing. These drones combine the benefit of vertical takeoff with the efficiency of a fixed-wing craft. In these environments, you can see where vertical takeoff is ideal, such as boat bows and dense urban environments. This leads into our next figure, which is a quick demonstration on propeller efficiency. While more motors increase system redundancy, the overall efficiency is reduced since there is less propeller area in the same given diameter. The most efficient system is a single rotor, or helicopter. Here's a quick list of some common sensors used in wildlife research. Radio telemetry receivers detect tracking tags, while RGB cameras are used to photograph areas. LiDAR uses laser range-finding technology to create an accurate scan of the area, where multispectral, hyperspectral, thermal, and NDVI cameras detect light outside the visible range. In the left image, you can see how a typical photogrammetry flight works. An aircraft captures images along a predefined path, and these images are stitched into a map with post-processing software. On the other hand, LiDAR works by emitting a series of laser pulses and measuring the distance from the scanner to the target. LiDAR is more powerful than photogrammetry in the sense that it can penetrate vegetation to capture the ground points seen here, but photogrammetry gives you a colorized, lifelike representation of the environment. One key benefit in LiDAR is that it can be used to detect nests under vegetation. Most modern drones have two-way transmission receive communication systems which send control, telemetry, and video signals between the drone and the controller. Some controllers operate on Wi-Fi frequencies and are subject to interference in densely populated areas. The next two figures show the difference between multicopter and fixed-wing flight controls. Here, we can see how multi-rotors use counter-rotating propellers and differential thrust to maintain stability, where here, we could see how fixed-wing aircraft use active control surfaces and a propeller and motor system to maintain its level flight. Mission planning requirements vary based on the overall objective of the flight. Mapping flights typically require extensive planning, whereas exploratory surveys are flown manually. On the right, you can see a variety of mission planning softwares typically used for wildlife surveys. Whatever the mission objective, drones capture tremendous amounts of data which require storage and post-processing. Post-processing the data increases the storage and time requirements for a particular project, and large area or repeat flights require extensive ground control surveys which tend to increase the project cost by a factor of 2 or 3. Post-processing can consist of photomosaicing, manually counting subjects, habitat comparison, and machine learning image recognition scripts. This image shows one of our hourglass photogrammetry targets located next to a wading bird colony. These are used as a static photo-identifiable point which can be used to reference photo data to a known ground coordinate system. Here's a quick overview of a typical drone mapping flight. The imagery, shown as green dots, were acquired over our study area by a fixed-wing aircraft flying in a raster pattern. These images were then post-processed into a map. This map provides very useful information since in one image we could capture a variety of different species surrounding the nest and also identify their locations. Here are some close-ups of some wildlife we could see in that image. We could see some birds, alligators, and even fish species surrounding the bird colony. Crocs and alligators are traditionally not scared by drones. However, they do notice them and change their behavior patterns. By using biomimicry, we could get closer to subjects without alerting them to our presence. Technological advancements in the recent years have enabled for innovation at a greater pace. Drones are now becoming an increasingly powerful tool for nature and conservation. Biologists are finding new ways to adapt these tools to gather insights on complex subjects, and have even become a source for new, popular shows like PBS's Spy in the Wild, where biologists use lifelike robots to enter a subject's habitat and interact with them in a natural manner. Continuing advancements in sensors, control systems, and battery technology will help further expand the usefulness and ease the operation of these powerful tools. Lastly, legal, ethical, and privacy considerations. Be cognizant and follow the local drone ordinances. Respect private property and individual privacy, and pay attention to your safety, yours, the public's, and your survey subjects, a key part of your drone operations, and be aware of your surroundings. We thank you for attending our introductory presentation, and we hope you enjoy the rest of the Crocodile Specialist Group Virtual Drone Workshop.